Hey everyone, this is the third part of Tuesday's lecture. And so I already uploaded lectures about question answering and about open domain question answering and retrieval. And so if you have not watched those yet, please go watch question answering first and then open domain question answering. This is the third part of the material that we'll be talking about in class on Tuesday, which is Retrieval Augmented Language Modeling. And so there's a broad appreciation that language models, very large language models, can store world knowledge because that knowledge is useful for performing their objective, which is to predict the next word or to predict mass tokens. And so the question is, can we make language models perform better at answering queries about world knowledge by augmenting a large language model with a retrieval model? All right, so why would we want to do this? Why would we think it could be a useful thing to augment a large language model with a retrieval model? Well, first of all, large language models tend to hallucinate, as the most probable next token isn't necessarily the one that maximizes the truthfulness of the generated text. And this problem gets worse with model size. And so you see this talked about a lot in the context of, say, ChatGPT, where I asked ChatGPT, what was the most influential paper on retrieval published in 2021? And ChatGPT gives me an answer that looks like it could be a paper on retrieval, but then if you go try to look it up, no such paper exists, and it just, predicted the most probable tokens in a language model sense, but it has no sense of, is this true or is this not? And this is really like, potentially a major problem for the trustworthiness of large language models. Relatedly, people would like language models to cite sources. Well, that's not what a language model does. It predicts the next token using kind of all the 175 billion parameters that it learned through predicting the next token during training. But that is how retrieval works. And so you'll see people like, why doesn't ChatGPT give me its sources? Well, it doesn't have them, but if you augmented them by retrieval, it would. It still might say something that is not consistent with the source, but it would be kind of more likely to be consistent with certain sources. It could allow the language model to use all of its capacity to learn language instead of using a bunch of its capacity to memorize facts. It could allow a smaller language model to more feasibly achieve the performance of a larger language model, since the facts it needed would be stored in an offline database. And it could allow the language model to incorporate new world knowledge at test time without requiring any additional training, which is important. So another complaint about large language models, it was trained at this point in time, and it still thinks that Donald Trump is president, or it's just, outdated in various ways. I just saw an article about the weaknesses of the weaknesses of GPT-4, which was just released. And again, it was talking about this, right? So if you could have a language model connect like with the internet, it would have more up-to-date knowledge. So with retrieval augmented language modeling, the language model is typically a transformer decoder like GPT or a transformer encoder decoder. We'll see an example called retro in a few slides. The retrieval model is typically a transformer bioencoder, and the design choices that you make with retrieval augmented language modeling entail specifying how the retriever and the language model interact. And so first, we'll talk about the first generation retrieval augmented language models, which are things like RALM, RAG, and Retro. I think Retro was published in 2022. So I'm saying first generation, but this space is moving quickly. And so I'm going to talk about Retro in some amount of detail, as I think it's a really great kind of illustration of how people, initially thought about retrieval augmented language modeling. And I'm going to use illustrations from Jay Alamar's amazing blog on Illustrated Retro. And so with GPT, you have this big language model that incorporates language information, but also a lot of world knowledge. Whereas the idea behind Retro is that the language model will be much, much smaller, and it will just have language knowledge. And then all the world knowledge information can be stored in an external database that the language model can consult in predicting the next token. And so what does this retro database looks like? well, you have a key, and then you have a value for each entry. And so the first text in the value is the neighbor, and neighbor is the text representation of the key, which is a vector representation of the neighbor, and then you have the completion of that text. And so you have a vector representation for Dune is a 21 American epic science fiction film, so on and so forth, and then you have the completion of that. What is in this database? Well, it's trillions of tokens from massive text, which is a combination of like web text and C4 and other large data sets. You see a lot of it is books. So don't think of this as Widener. I don't think it's Widener, which is mostly under copyright. It would be more like public domain books. A bunch of stuff scraped from the web. News articles is given a weight of 10% here. This comes from a corpus called Real News that we've worked with quite extensively. Wikipedia and GitHub. So this is breaking it down more by language. This is overwhelmingly going to be English, but I mean, Retro is multilingual, but still, you know, the lion's share of it is English web. And that's going to matter for what kind of world knowledge is encapsulated in this database, right? I mean, they call it world knowledge, but it's certainly going to be very skewed towards knowledge in English on the public domain internet. And so this is showing the document length distribution. Not surprisingly, you know, the books tend to be longer. They look at training set toxicity. So, you know, Wikipedia is not that toxic. The internet is more toxic in general, like the massive web text. Okay, so these are the top 20 domains in the massive web corpus. Science Direct, NCBI, which is academic articles. Facebook is a big one. Academia.edu, that's academic papers. Quora is another big one. YouTube comments. Wikipedia is there. Reddit, Medium, Wiley, GitHub, Stack Overflow, etc. This is the distribution of languages that are not English. So again, the lion's share of it's going to be English, but it gets some stuff in other languages. I mean, not a lot, and a big share of it's Hindi. But there is some representation of world knowledge from non-English languages. That's obviously going to be a limitation if you're thinking about using kind of a pre-trained model for whatever your application is. This is not massive text, but this is a highly correlated data set called the PILE, which is a public domain massive text data set that I really like this graphic. And you see what a big part PubMed is. You know, I saw something about GPT-4 where a doctor was saying, oh, I can't believe it has so much medical knowledge. But it kind of makes sense given how much of a role PubMed plays in the training. You see archive there, free law, US Patent Office, Stack Exchange being a pretty big share. Look at GitHub there. And so this kind of gives you some sense of what large language models were trained on, and also more specifically, you know, this is the type of stuff that's in that world knowledge database. So back to Retro. So to query the database, we take an input the Dune film was released in and compute a sentence embedding for that just by taking the average contextualized token embeddings, just like we saw when we talked about sentence embeddings a couple of weeks ago. And then we use that to query the database. And we do that with an approximate nearest neighbor search to retrieve the two nearest neighbors whose text is going to become part of the language model input. And so the input is the prompt, the Dune film was released in, nearest neighbor 1, which is the text kind of that's closest to the vector representation of the input and its continuation, and nearest neighbor 2. And that gets fed into Retro, which gives the next token, 2021. And so let's break down what this looks like. A retrotransformer is an encoder-decoder transformer model. And it has an encoder stack that's used to process the neighbors and a decoder stack that's used to process the text prompt. And so specifically, the encoder has standard encoder transformer blocks, which are self-attention plus a feed-forward neural network. And there are, whereas in the decoder, there are two types of decoder blocks. There's standard transformer decoder blocks, like you have in GPT with attention and a feed-forward layer. And then you also have the retro decoder blocks, which have self-attention, but also chunked cross-attention to the encoder stack. And so specifically with the encoder, it works just like the transformer encoder models that we already saw. You feed in your two nearest neighbors and you get the key and value matrices for those, and those are going to be used for cross-attention. All right. And then with the decoder stack, you have standard decoder blocks, and those apply causal self-attention to the prompt, so they can only attend to the previous tokens and pass that through a feed-forward layer. But then you also have these retro blocks, which are every third block starting from layer 9. So layers 9, 12, 15, up to 32 are retro transformer blocks. And what do the retro blocks do? Well, they have cross attention to the retrieved neighbors. And so you can see here, they're kind of allowing you to attend to the specific date that you need to predict the next word in this query. Now, a potential issue with evaluating the performance of this is that if your query literally appears in your external database, which it might, since lots of benchmarks are found in C4 and in other kind of large web text data sets, then obviously you're going to be able to complete it because you just saw it. And so they give examples where this happens in the appendix, and they say this doesn't drive the performance of their model. But I do think it's worth keeping in mind. So this is what we did on Real News, which you saw, the news part of their data set had a 10% weight. And so hashing, that's literally using exactly their method to deduplicate, which they argue kind of, means that this isn't really an issue. But you can see with the neural method, we find way more noisy duplicate clusters. And most of them are true positives and not false positives. And so, I don't think this kind of invalidates in any way, how kind of powerful the architecture is, but it's just something to keep in mind when you're looking at performance, that you might want to think about, well, is that benchmark likely to literally be in the database? Which then, of course, it wouldn't be surprising that it performs relatively well. Okay. So that's kind of the first generation retrieval augmented language models. Now I want to say a word about second generation retrieval augmented language models. So retro and other early models, and by this I mean models from a year or two ago, froze the retriever and trained the language model. And it was argued that, training the retriever would just be way too costly because of reindexing. Because if you train the retriever, then at each step, your embeddings that you're querying are now out of date because they were created with a retriever from a previous step of the training. And so that's going to cause problems. It's going to cause things to be misaligned. And so you're going to need to update the index. And so you're going to need to re-embed everything and re-index it all. And that's going to be pretty costly. And so kind of initially it's well, we're going to train a language model because this re-indexing thing makes training the retriever really costly. But the second generation of retrieval augmented language models instead freeze the language model, and they focus on developing a retrieval framework that will play nicely with a very, 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 very large frozen language model. So GPT behind an API. And they aim to really take advantage of the capabilities of these very, 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 very large language models. And their motivation is that these very, 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 very large language models are just too good to forego, even if it means we can't tune them because they're a black box behind an API. And so very recent literature, notable contributions include Replug and DSP. And so Replug treats the language model as a black box and augments it with a tunable retrieval model. Unlike prior retrieval augmented language models that train the language model with cross-attention mechanisms to encode the retrieved text, Replug just prepends the retrieved documents to the input for the frozen language model. And so instead of having what you saw with Retro, where you pass the retrieved text into the encoder, and then you have your decoder with your query, and you have this cross-attention mechanism, instead you're just gonna like take the retrieved text and add it to your prompt. Another insight of Replug is that the language model can be used to supervise the training of the retrieval model. And they find that Replug improves the performance of GPT-3 by 6.3% on language modeling. And so this is their depiction. So previously, you have jobs as the CEO of, pass that to a frozen retriever, get the context, and then pass that to a language model that you trained. And that language model will be small in that it has less than 10 billion parameters. Whereas Replug, you pass that to a retriever, which could be either frozen or trainable, get your context, and then you pass that into a black box language model, which is going to be a language model with more than 100 billion parameters. Okay, and so the Replug framework more specifically, you have jobs as the CEO of, pass that to the retriever, get your retrieved documents, and you just append each of those to your query, pass it into GPT, and you'll get a probability distribution over the next words, and you just ensemble those probabilities and choose the most likely next word. So how do they train the retriever? Well, the basic idea here is that you have a retriever likelihood. What's the likelihood that each of these retrieved documents has the answer to your query? And you also have a likelihood from the language model, and that you want to minimize the KL divergence between those two. And so specifically, you compute the language model probability of the ground truth output given the input context and the document. And the higher the probability, the better the document is at improving the language model's perplexity. And so you can update the retrieval model parameters by minimizing the KL divergence between the retrieval likelihood and the language model's score distribution. What we want is that the retriever finds documents that result in lower perplexity scores for the language model. And so this is like, again, on the note of self-supervised training of retrievals, self-supervised training of retrievers, here they're using the language model to provide the supervisory signal for training the retriever, such that they're incentivizing the retriever to choose documents that make it more likely that the language model can predict the next word correctly. Because the parameters in the retriever are updated during training, the previously computed document embeddings are no longer up to date, and hence it is necessary to rebuild the efficient search index using the new embeddings every T training steps. And so Replug can be used with a variety of language models to improve performance. The authors point out that the method is not very interpretable and that it is unclear whether the language model's predictions rely on parametric knowledge or retrieved knowledge, which could still be an issue. GPT gives you an answer and it cites some retrieved documents as its sources, but that doesn't necessarily mean that the answer came from those retrieved documents. It just means those retrieved documents were added into the context, and it might still hallucinate something. And that could kind of be an issue in terms of like what it means to cite your sources. In an analysis of examples in which Replug results in a decrease in perplexity, they find it's most helpful for rare entities. And so their example is a Chinese poet, right? Which again goes back to, this being trained on disproportionately on the English internet, right? And this this Chinese poet probably wasn't mentioned very much in the training data. And so it makes sense that this retrieval enhanced language modeling would be helpful. All right. The second thing, the second framework that I want to mention is demonstrate, search, predict. This isn't even really like a model so much as a framework. And so if you wanted to take kind of the simplest possible approach to retrieval augmented language modeling with a frozen retriever and a frozen language model, you would just insert the retrieved passages into the LM prompt, which is essentially what Replug does if it freezes the retriever. And so DSP aims to develop a more sophisticated framework for combining a frozen language model and a frozen retrieval model that, in quotes from their abstract, relies on passing natural language text and sophisticated pipelines between the language model and the retrieval model. And so it's quite reminiscent of chain of thought prompting in that it breaks problems into smaller transformations that it argues can be handled more reliably by the language model and the retrieval model. And they find it significantly improves performance relative to vanilla GPT 3.5 and a standard retrieve then read pipeline. And so this is their motivating example. How many stories are in the castle David Gregory inherited? The vanilla language model hallucinates a fictitious castle. The retrieve then read model retrieves the wrong document, and so then it gives the wrong answer, whereas their multi-hop DSP program breaks this question down. Which castle did David Gregory inherit? David Gregory inherited Kinnerdy Castle in 1664. How many stories does Kinnerdy Castle have? It's a tower house having 5 stories. And then it feeds kind of this into the language model, and then it gets it right. So this is their model architecture figure. I think it's very helpful to break this down. So the meat of this is the search part of it. And the search part of it has a few things. It has this multi-hop search where they're breaking down the question into sort of chain of thought prompting. Another key part of it is it's summarizing the answer, right? And so you're getting kind of these multiple contexts returned, and that wouldn't necessarily all fit into a prompt, but they're actually using the kind of remarkable summarization capacity of GPT to summarize the retrieved document so that they can fit it into their prompt. Okay, this should say predict, and so then they're just gonna, my task is to answer questions using web documents. There's a demonstration, there's a context, there's a question, and then they have this rationale from chain of thought prompting, and they wanted to provide the answer. And this is the demonstrate part, which is utilizing kind of this phenomenon known as in-context learning, where you can tell a very large language model, do this, and then it does that without needing to tune its parameters. And so this has kind of been one of the kind of most, emphasized features of very large language models, that you can give them examples and then ask them to perform the task. And oftentimes they can do it, or at least kind of do it. And so they demonstrate this whole multi-hop procedure to GPT. And so the main takeaways: in context learning, where a large language model performs a task just by conditioning on input-output examples without optimizing any parameters, is a really powerful tool. Chain of thought prompting provides information that the models can more easily digest. And we also see that rules make a comeback, and that really you're designing rules about how to prompt this that kind of make use of the in-context learning and the chain of thought prompting and the summarization capabilities of GPT to do something really powerful without having to train a model at all. And I think this is like one of my kind of favorite examples from the prompting literature, in that kind of it shows how to achieve results that improve over vanilla GPT, but without having to train anything, just by kind of designing the prompts and the instructions that you give to GPT, how you retrieve as well in a way that is easier for these models to digest. So putting the language model behind an API and having it interact with an external retrievable database like the internet is clearly the path for commercializing AI. And right now there is a huge race on to see who's going to do that the best, the quickest, and become, the technology firm of, the future. And so this is obviously kind of huge, and we see all of this, starting to play out in real time. Things like Bing connecting to the internet. And I think, we'll probably see a lot more of this retrieval enhanced large language modeling, because it does, at least try to address some of the problems that we have, like them quickly becoming out of date, and, just maybe helps with the hallucination, maybe helps with citing sources, although there's still no guarantee that those sources are what generated the answer. But it helps with kind of some of the most common critiques of chatbots. So in coming lectures, we will see how retrieval can be used to approach a number of social science applications. And in many of these contexts, it's really hard to imagine that a frozen GPT or other massive language model and a frozen retriever could be on par with self-supervised or supervised training on the target domain, which can differ pretty drastically from the data the model saw in training. So oftentimes we do things in languages that are not prevalent in training corpuses that are historical. Like, there's just lots of things that are different about our applications than about a commercial application. But I still think that there's likely some really powerful academic applications to these approaches, and I'll really look forward to discussing this more in class on Tuesday. So that's all I have on retrieval augmented language modeling. I hope everyone enjoys the rest of their spring break, and I will see you guys next week.